Hello students, in this video we are going to discuss about short circuit test. Short circuit test is conducted on transformer and it is used to measure the copper losses of a transformer. As we know, transformer losses are mainly divided in two categories, copper losses and iron losses. So in this video we are going to discuss about the short circuit test, and this test is utilized to measure copper losses. Copper losses basically is the heat loss which occur in transformer windings. While current flowing through the transformer winding, a I square R heating takes place across the winding resistance. As we know, transformer winding current depends upon the load. So we can say that the value of copper losses varies as the load changes on the transformer. Or copper losses are also known as load-dependent losses. The value of copper losses is maximum when transformer is at its full load condition. And as we move from full load to half load, similarly, the value of copper losses also reduces as the square of the load current. So from full load to half load condition, the copper loss is reduced to 1/4 of its initial, 1/4 of its full load value. And at no load condition, the value of copper losses can be considered to be 0. For measurement of copper losses, we perform short circuit test. And here we can see the experimental setup of short circuit test. In short circuit test, on primary side of transformer, we connect an ammeter and wattmeter and a voltmeter. Whereas on the secondary side of transformer is short circuited with the help of a thick copper wire, or what we can do, we can connect an additional ammeter on secondary side. We can connect additional ammeter here like this. And the purpose of this ammeter is to measure the secondary current. So by measuring current on both the sides of transformer, we can easily calculate the transformation ratio K. The procedure for short circuit test is like this. This test is conducted on rated current. Important parameter while performing this test is rated current. So we increase the supply from the variac in very small steps from 0. Reason is, as the transformer secondary is short circuited, so we have to keep in mind that we cannot apply the normal or rated voltage directly. Here we increase the voltage in very, very small steps starting from the 0. As the voltage is slightly increased in very small step, what happens is, with the application of very small voltage, a weak magnetic flux is developed in the primary side and the transformer action takes place. Due to this transformer action, flux links with the secondary winding, and in secondary winding, a considerable amount of current starts flowing. The reason behind high secondary current is, in secondary winding, there is no load impedance, and due to short circuit, whenever a small voltages appear across secondary windings, this small voltage is capable of developing considerable amount of current. Or in other words, we can say that under short circuit condition, with the application of very small voltage, there is a rapid increase in winding currents. So if we keep on increasing the voltage in small steps, what we can see, the rated current of the primary side can be achieved at a voltage which is hardly around 8 to 10% of the rated voltage of primary side. Under short circuit condition, with the application of very small voltage, we can achieve the rated current. So in this scenario, what happens is, as secondary side of transformer is short circuited, so whatever is the power taken from the source, it is dissipated in the form of losses. But as the applied voltage is very small, so we can say that due to application of small voltage, the magnetic field available in the transformer core is also going to be very small. So under short circuit condition, because of weak magnetic flux present in the core, we can say the flux dependent losses or our iron losses are going to be very, very small. So while performing this test, we can assume that as the applied voltage is small, so iron losses can be neglected, and it is assumed that whatever is the power supplied to the primary side, the entire power is dissipated in the form of copper losses. And as this test is conducted on rated current, so by the wattmeter reading, we can directly find out the copper losses of the machine. So this is the procedure of short circuit test. Now, while performing short circuit test, we have to keep few things in mind. The important point is we always prefer to conduct this test on high voltage side of a transformer. This we can understand with an example. Let we have a transformer having following ratings. The kVA rating of transformer is 1 kVA and the voltage rating of transformer is 500/100 volt. So if we have to conduct short circuit test on this transformer, so it is advisable to conduct this test on high voltage side, that is on this side. Reason is the rated current of both the windings of transformer is on side high voltage side, the rated current is 2 ampere, whereas on low voltage side, we can say it is 10 ampere. So if we conduct short circuit test on high voltage side, we can see that we have to conduct this test for a current of 2 ampere, and this 2 ampere current will be available around a voltage which is 8 to 10%. Say we are achieving rated current on application of 10% of rated voltage under short circuit condition. So while performing this test on high voltage side, we can achieve this current of 2 ampere with the application of voltage around 50 volts. So here we can see that the voltage and current both lies in the normal operating range. But if we conduct the same test on LV side, what happens is on LV side, the rated current is 10 ampere, and this 10 ampere we have to handle at a voltage level around 10 volts. So this is the main problem of this test, that if we conduct this test on low voltage side, the winding current becomes too high and the corresponding winding voltage becomes very small. And it is almost impossible to have such equipments which we can handle at a low voltage. So if we conduct this test on low voltage side, what happens is the winding current becomes very high and corresponding winding voltage becomes very. So it is almost impossible to have instruments which are capable of handling high current at its corresponding low voltage levels. So this is the reason why it is advisable to conduct this test on high voltage side and low voltage side is kept short. Now, moving ahead, from the data of this short circuit test, we can also calculate the parameters of equivalent circuit. Let us consider these are the three readings of my short circuit test. This is the wattmeter reading, this is the voltmeter reading, and this is the reading of ammeter. Now using these three readings, we can easily calculate equivalent winding resistance and equivalent winding reactance of the transformer refer to the side at which this test is conducted. And the calculations are pretty simple. By wattmeter reading divided by square of ammeter reading, we will get RO1, which is the equivalent winding resistance, which referred on the side at which this short circuit test is conducted. And by using these two parameters, we can also calculate the voltage regulation of the transformer. So this is how we conduct short circuit test. This is the reference used for making this video. So this is how we can perform short circuit test on a transformer and determine its copper losses. Thank you.